This is the OpenHPI course Linked Data Engineering, and this is part 1, where we learn how to query RDFS with SPARQL. Okay, SPARQL is the query language here in the semantic web technology stack, and therefore with SPARQL you will be able to query RDF graphs, and how this works we will see in a few seconds. So first, SPARQL is communicated in an extra protocol layer over HTTP, the regular web protocol. Usually this is a client-server interaction, simply because of HTTP is a client-server interaction. You have a SPARQL endpoint as the server endpoint, which is nothing else but a database which contains triples. And you have a client, and the client accesses via HTTP the SPARQL endpoint. And SPARQL defines a special protocol that enables you to put the SPARQL query as part of the HTTP protocol URL and transmit it from the client to the server. And usually the server then provides some kind of a front end, a user interface, where you can formulate your query, interactively submit your query, and then read your results. So this is the way how SPARQL as a query language is working. Later on we will also have a look at this SPARQL protocol layer. Okay, SPARQL is an acronym. It stands for SPARQL Protocol and RDF Query Language. And this, of course, is a query language for RDF graph traversal. We will see that, or we know that RDF builds a huge graph, and of course this graph can be traversed, and there is a special query language which makes use of exactly this graph structure. We will see how this will work. So this is the SPARQL query language specification. More than that, there is then also the protocol layer, which defines how SPARQL can be used with the help of the HTTP web protocol. And then, of course, the return format, so the result of the SPARQL query, is, for example, here given in an XML output format, for which also a specification exists, and we will also have later on a look at that to understand that. Because it's not only possible, of course, with this web client to access the SPARQL endpoint, you can, of course, also write programs, and the programs can use the HTTP communication to query SPARQL directly at the SPARQL endpoint, and then, of course, they must know how to read and how to understand the return format, which usually is given in this XML output format specification. SPARQL is standardized for a long time, so the new standard SPARQL 1.1 was published in March 2013. And if you have ever wondered how a data query language is working, it's of course pretty similar to what you maybe already know from databases. So if you know relational databases, you have certainly heard of SQL or SQL as a query language. And SPARQL for sure is inspired by SQL. So lots of things will look familiar to those of you who are already familiar with SQL. Okay, so let's start. First, if we want to query, we need something like variables. Because in variables, of course, return values, so the results will be transported. SPARQL variables usually then are bound to RDF terms. And usually to make clear that this now is a variable and another thing is some RDF term, you distinguish the variables by putting a question mark in front of the variable name. So as you see here, for example, question mark title, question mark author, or question mark address. These are simply SPARQL variables. Okay, and the query itself works pretty similar like in SQL, like in SQL. So to get data from the SPARQL endpoint, you have to formulate a so-called select statement. So the operation you perform is a select operation, select statement. It's also available in SQL. And then you say what kind of variables you want to have filled with data. And there, for example, in our example, you see select title, author, and published, which again would then be the variables that should be filled for the return format. And in the return format, usually the SPARQL query returns a query result as a table, like you are used to do that in relational databases. So you would have a table with 3 columns, title, author, and published, which will be filled with the results, with the SPARQL results. So This is the most simple thing in SPARQL. Now, how does SPARQL work? SPARQL is based on an RDF turtle serialization. We have already talked about turtles, so you know how to read that. And what we are doing, we are defining so-called graph patterns. And then SPARQL works as a pattern matching algorithm. What is a graph pattern or a triple pattern? This is simply an RDF triple which contains one or more variables at arbitrary places, so as a subject, as a property, or as an object. So a graph triple pattern is nothing else but turtle plus variables. Look at the first example we have here. So this is a triple where the first position, the subject, and also the object are variables. And we only specify here the property as a fixed RDF term, and this would be DBO, which stands for DBpedia ontology. We have talked about all these namespaces, capital, which would mean we are looking for countries and their capitals, which means we are looking for triples where the subject is a country and where the object is the capital. And definitely what our graph pattern matcher does is it compares whether the property of the returned really is DBO capital. And only those triples which contain DBO capital as a property will be returned. So this is a graph, basic graph pattern. This is how the pattern matching really works. You see here country, DBO capital, capital. And then we have the RDF graph where there are lots of countries and stuff like that. And it picks exactly these triples which contain here DBO capital as a property. So you see these fixed parts of the graph pattern, they are compared to in the RDF graph and will be returned. And the variables then will be filled according to the other parts of the triple, which in the triple pattern are identified via the variables. So country would be the subject, capital would be the object, and they will be returned in the result. This is how SPARQL works, and this is pretty simple, isn't it? Okay, but this is only one simple pattern. You might think of more complex queries. And the most simple thing to create complex queries is to conjunctively combine several patterns. It means if you simply write one triple pattern and add another triple pattern, then both are conjunctively tested, which means both must be fulfilled by the result that matches exactly these patterns. So for example, here we have find countries, their capitals, and their population count. And what you do here is, of course, we have the first line that we know already, country, DBO capital, and capital. And then we add another triple pattern, which we say, yeah, it should be the same country. And then we use another property, which would be here then DBO population. You can look this up in the DBpedia ontology. And then another variable, which then would be population. And then, of course, countries, their capitals, and their population will be conjunctively combined and returned. So both patterns must match with the variables given there. Another more complex example. So what we are doing here in the very last example is we have given a faux URI, so a friend of a friend URI, which means this is some URI of a person, and the person, of course, has some affiliation and other data, personal data, which is mapped to exactly this person and encoded in its faux file. And we are querying here a faux file, and therefore we are using as the subject the name or the faux URI of the person, and we want to find out the name, which means we also fix from the faux vocabulary the faux name as a property, and then the first variable would be the surname that we want to have. So given a faux URI, find the name of a person, this is the very first triple pattern, and her friends. So how do we do that? Of course, we can add another triple pattern, which then would have the same faux URI in the front. Then the friends means we are using faux knows, which is the property which connects a person to their friends that they know. So faux knows is the property. And then the second variable would be friend in the object place. And you see here we can make use of the turtle own abbreviation. So we are closing the first triple pattern not with a period but with a semicolon, and therefore we can leave out the second subject. And then, of course, we do not want to have the URI of the friend, which would be encoded in friend. We want the name of the friend. So therefore, we conjunctively add another triple pattern. This is then the third one, where we say friend should have the fourth name, friend surname, which means then, in the end, our result would consist of the name or surname of the given person, then the friends of the given person, and of course the name of the friends of the given person. So this is how a more complex SPARQL query pattern is combined and how this works. Of course, if you do this then in real life, SPARQL is a bit more complex. First thing, of course, it works like Turtle, as I told you, but of course SPARQL must know about the prefixes that we are using, so therefore you also have to do prefix definitions like you are used to do this in Turtle. The only difference that you see here is prefix definitions are not closed by a period here in SPARQL, so the prefix definitions simply end with the URI that you see here. So you have the fixed keyword prefix, then you have the prefix of the namespace that you are using, and then the URI of the namespace that you are using. So we have several prefix definitions, and then comes our select statement. What do we want to do here in this example? So this example is about searching all authors and the title of their notable works in DBpedia. So we are creating a select statement, and we want to have the author name, and we want to have the title. So these are the two variables that should be returned. But first thing, of course, here are the namespaces. Then here we specify the output variables which should be returned. And then, and this is pretty similar also to SQL, we have another keyword that we did not know up to now. This is the from keyword. There we specify which graph of the available RDF graphs of the SPARQL endpoint will be queried. So this specifies the graph to be queried. And in our case, this is the DBpedia graph. This is not necessarily the URI of the SPARQL endpoint. This is the name of the graph that we are querying at the SPARQL endpoint. So we will see that there is a bit of a difference. And then in the third part, the where part, we specify all the graph patterns that should be matched. So let's recollect what we want to do. We want to search all authors and the titles of the notable works. And we want to do this in DBpedia. So first of all, if you look at the triple patterns, the first triple pattern states, okay, subject should be the author. And of course, it should be of type DBO writer, which means this is somebody who has written some work. So definitely an author. DBO writer, again, is a class which comes from the DBpedia ontology. Second thing, we do not want to have the URI of the author, we want to have the name of the author. So therefore, second graph pattern, author, RDFS label, author name, which means this is the label of the author, usually the human readable name. Then we want to have the titles of the notable works. So first, next connection we have to do is we have to go from author to the notable work via the DBO notable work property. And then we have as an object the next variable, which is work. And of course, we do not want to have the URI of the work. We also want to have the label, and therefore the last pattern that we combine here is work, RDFS label, and then the title. And as you see here, author name and title will be returned as the output variables. This is over here. And these are then character strings which are defined here as RDFS labels. This would be a perfect, simple SPARQL query that we can try out, for example, at the SPARQL endpoint of DBpedia. And we will do this shortly, but first I want to show you a few more keywords that you can use, similar in SQL and relational databases. So for example, if you want to have the same query, but you want to have, of course, the results ordered in ascending order, so ordered by their names, and you want only to show the first 100, so you want to set a limit on the first 100 results. And you do not want to start with the first one, you want to start at position 10. So it means you define an offset of 10. You do this in a quite simple way. So first of all that you see here, you have so-called solution sequence modifiers in SPARQL. First thing is you specify with order by a way how the result should be ordered. And then you have the possibility to say ascending, ASC, or descending, DESC. And then you can specify one or more variables according which the result, the output, should be ordered. And here it should be ordered in ascending order by the author name. Then you can specify, give me only the first 100, which is limit 100. And then you can say where to start, and you should start at position 10, which is offset 10. Quite simple. You see here in the slides that we have always a link given here, which says query SPARQL endpoint. So if you click on that, if you click on that, try it again, then you will end up here in the SPARQL endpoint, and you see here this is the SPARQL endpoint of the DBpedia. So you see here dbpedia.org SPARQL and then question mark. So this is the DBpedia SPARQL endpoint. And behind the question mark you see the entire query, which stands here in this window. You see here the entire query. And this is encoded here in the URL. So it's here in URL encoding. This is the entire query. So it's pretty long, as you see here. This is the query. Okay, but you see here exactly what we had on the slide. We have the prefix definitions, the select, the output variables. We select it from dbpedia.org. And then we say, okay, author, DB type, RDF type writer. Then we want to have the RDFS label. And then we say notable work, and then we say from work RDFS label title. So we want to have the title. This should be ordered by author name. Limit 100, offset 10, and here is the button that you should press, run query. And you see here the return or the returned result will be a table with two columns, and the first column is author name and the second column is title. And you see here then the names of the authors and the names of titles of their books. And it's only the first 100, and we start at position 10, so we must now believe that this is at position 10. Okay, so let's return to our slide. So this was the first simple SPARQL query. Another thing I wanted to show you also related to the SPARQL query to make them a little bit more complex would be besides posing simple matching patterns for the graph that is traversed, for the RDF graph, what you can do is you can additionally specify filter conditions, filter constraints, which means additional conditions which the displayed results should fulfill. Let's have a look at that one. So it's exactly the same query that you see here that we had before. The only thing is here at what we want to have is we have an additional variable which is pages. And we say here work DBO number of pages, which means we want to have the number of pages of the work of the author, of the notable work. And there comes then the filter condition with the keyword filter. And then here in brackets, in parentheses, sorry, we have pages should be greater than 500. So this specifies constraints for the result and means we only want to have those notable works displayed which have more than 500 pages. And this time we do not order it, we simply put there a limit which is limit 100. Okay, let's try this out. We simply click on that. We have here the SPARQL query again and we query it, and you see the result then will be author name, title and pages. Pages you see here. This is specified as a positive integer. This is a typed literal in the sense that this is of course 530 is a character string, and then you put on there a data type, and the data type is here XML or XML schema definition, positive integer. So this should be interpreted as an integer. And you see here all the numbers that you see here are usually greater than 500. And of course you are free to play around with that. So for example, if we go back and would write here instead of 500, 1000, you would only see books with more than 1000 pages. And you see here 1120, 1074. So yeah, Stephen King obviously writes long books. You see here then the result according to your filter specification. So this is the possibility to filter the results in an additional filter condition. What else can you do? Of course, together with a filter condition, you have several operators that you can use on the variables, for example. You have unary operators, like, for example, if the result is a Boolean, you can reverse the Boolean and can, of course, complement it. If it's a numeric, you can interpret it as a positive or a negative numeral, and you can ask whether this variable is bound to an RDF term or not, which means whether this variable has any result or whether it has no result. So then you test here simply, you say bound A, and if A is bound, if there is a result, then the result is true, otherwise it's false. And you can ask whether the variable A in the end is a URI. You can ask whether this is a blank note, or you can ask whether this is a literal. Sometimes this is quite handy. And of course you can here do data conversions. You can for example, convert a URL or another literal to a string, and you can test here if it's a string for the language. So what kind of language identifier is given there. And of course you can also ask, is there a data type given with a data type operator. So these are the unary operator constraints that are possible in SPARQL. Let's try to apply this in a final SPARQL query. So what we do here is we want to filter our results only for English labels, which means we want only have the English labels of the authors and also the English labels of the titles. So what are we doing is, after we have selected here the author name, which is the label of author, we put in a filter condition and say here, author name, the language of it should be English. So this is the abbreviation, the acronym for English. And then of course also we do the same thing here for the title. And we say here, filter, the language of title should also be English. Let's try it out. So this again is the query, and we try it out. And we see here now that, of course, you see there are only names, labels, which have here the postfix or the language identifier EN, which means English. So these are only the English names of the title. Oh, this is interesting. So there are 3 names of people who have written a novel which has the name Anna Karenina, which, as far as I knew, was from Leo Tolstoy. So you see, you can learn a lot of the data of DBpedia. These are only the first 100. I invite you to explore the data that is out there, because now, with the help of SPARQL, you simply can do that. Okay, so go ahead and explore. How should you start your exploration? So first of all, you might ask, okay, I'm not so familiar with DBpedia. How should this work? Choose any arbitrary topic and search it in Wikipedia. From Wikipedia, you simply get to the DBpedia identifier. You see here the 2 URIs of George Orwell. This is the George Orwell page, famous author of 1984 in Wikipedia, and here it's the according page in DBpedia. You see here how the pattern works and how you can get from the Wikipedia identifier to the DBpedia identifier. Next thing you should do, you should browse a bit there. So simply click on that George Orwell page and you will see what kind of properties are available for George Orwell, who is an author, for example. What kind of type definitions are there? So what kind of classes does George Orwell belong to get a bit familiar with the knowledge that is represented in DBpedia. And then, of course, if you find something interesting and have an idea developed for our own SPARQL query, go to the DBpedia endpoint and try to put there your own SPARQL query, according to the patterns we have already learned. Okay, and in the next part of the lecture, you will learn how to make even more complex queries with SPARQL.